Welcome back, everybody. This is our second video or second session in JEE Mains previous year questions for chapter Atoms of class 12. Before this video, we have made one video in this series, and that video is available on our channel's playlist section. We have also started similar series for NEET. So if some of your friends are preparing for NEET or you want some additional practice, then you can watch those videos also. And if you find these videos helpful, useful, then do press the like button, share them, and subscribe to our channel. Like to support us, scan the QR codes in front of your screen. So with this, let's start today's video. In the previous one, this was the last question which we covered, and that was the 7th. Today we are going to start with question number 8. The energy required to ionize a hydrogen-like ion, hydrogen-like it is mentioned, on its ground state is 9 Rydbergs. What is the wavelength of radiation emitted when the electron in this ion jumps from second excited state to the ground state? So here it is mentioned that energy required in terms of 9 Rydbergs. Now let us discuss the units first. Now we know that energy is Hc by lambda. Now value of Hc that we commonly take, that is 1240 electron volt nanometer divided by lambda. So Hc has a units of electron volt nanometer. Now we know that R, that is Rydberg, has a unit of meter inverse. So if we multiply this, here we have nanometer, basically meter, and here we have meter inverse. So if we multiply both of these two, HCr, this has units of electron volt. So basically HCr has a units of energy. So the term here, the term mentioned here that energy required is 9 Rydbergs. It's actually 9 HCr units, or that is the actual unit here. Now for hydrogen-like element, we know that En is equal to minus of Z square into 13.6 electron volt by N square. That is the actual formula for hydrogen-like element. And now it is mentioned that energy required is 9 Rydberg, that is basically 9 HCr. So I can equate I can say I will ignore that negative sign. So HCr 9 into 13.6 should equal to minus, sorry, I'm ignoring negative sign, Z square by N square into 13.6. Now, how I got this 13.6? This I got from here. For hydrogen, EH, let's say, for hydrogen, Z will be 1. So this will be minus 13.6 electron volt divided by N square. Oh, sorry, I forgot N square. I will also get N square here. And this is for hydrogen. And for hydrogen, I like that is 9 Rydbergs or 9 HCr, that is 9 times of the hydrogen. So that's why I wrote 9 times of the hydrogen is equal to Z square by N square into minus 13 into 13.6. So this 13.6 gets cancelled, N square gets cancelled, and from this we will get Z is equal to plus minus 3. So value of Z is 3. Now we have to calculate wavelength for the transition from second excited state to the ground state. So means we would transition N3 to N1, and for that we will use that 1 by lambda is equal to R, and here we will also have Z, Z square. We also have Z square here. Z square R 1 minus 1 square by 3 square. So this will be 9R into, here we have 9, here we will have 8. So that is basically 8R. And from that lambda becomes 1 by 8R. Now let's substitute the value. So that will be 1 by 8 into 109 into 737. Yeah, 737. 109, 737. And this will be approximately equal to 11.39 nanometer. And that is comparable to option B for us. The only important thing in this question is this Rydberg unit. And what is Rydberg unit? If you consider it as R, then it will be wrong. Actual Rydberg unit is HCR, and that can be assumed as R dash. Now let us move to the next one. The first member of the Balmer series of hydrogen atom has a wavelength of 6561, the wavelength of the second member of the Balmer series. So for Balmer series, we know N1 is 2 and N2 can take any value greater than 2. So 1 by lambda 1 will be equal to R 1 by 2 square minus 1 by 3 square. This is the first member of the Balmer series, and that's wavelength is 6561 angstrom. So 1 by 6561, and that is an angstrom. R into 1 by 4 minus 1 by 9, that will be 36 and 5. Now for the second member, 1 by lambda 2, we will have R into 1 by 2 square minus 1 by 4 square, and that will be equal to R. When we solve this, we will get 3R by 16. So that is 1 by lambda 2. Now what I can do, I can divide both of these two, and what I will get 1 by 6561 divided by 1 by lambda 2, and that will be equal to R gets cancelled. Oh, sorry. R gets cancelled, and we have 5 by 36 and 3 by 16. So that will go on 4, that will go on 9. And here I will have lambda 2 by 6561 is equal to 20 by 27, and lambda 2 is 6561 into 20 by 27. Now this is 12, 18. We can cancel it both by 3. So this will go on 9. This will on 2, 1, 8, 7. Now again 15 and 3, 18. Again we can cancel it by 3. So 3, 7, 2, 9. And again it can be cancelled by 3. So that will be 24 into 3. So if we multiply now, that will be 6844860, and that will be in angstrom, because this value was in angstrom. And if want to find it in nanometer, that will be 486 nanometer, because answer is required in nanometer. So 486. Moving to the next one. The time period of revolution of electron in the ground state orbit in hydrogen atom is given by this value. The frequency of the revolution of the electron in first excited state. Now, we know from the Bohr model that time period is proportional to n cube by z square. So we can use this to calculate the values, and here z is the atomic number for the hydrogen-like atom or element. So from this T1 by T2 will be basically equal to N1 by N2 whole cube. So we have first time period, and we have to calculate second time period and then calculate frequency from that second time period. So T1, that is 1.6 10 to the power minus 16 divided by T2 will be equal to For ground state, N1 is 1, and for the first excited state, N2 is half. So that's Q. Now this can be written as 1 by T2 is equal to 1 by 8 into 1.6 10 to the power minus 60. Now 1 by T2 is basically frequency, because frequency is inverse of the time period. So F2 will be equal to here, that can be written as 10 to the power 16 divided by 8 into 1.6, and I can write it like 100 into 10 to the power 14 divided by 8 and 1.6. This will cancel on 25, this will go on 2. So 25 by 3.2 into 10 to the power 14, and if I approximate it, let us write it like 24 divided by 3 into 10 to the power 14. I'm approximating it. So that will be 8 into 10 to the power 14, and that is option B for us. So option B is the right answer. Now let us move ahead. An excited helium plus ion emit two photons in succession with wavelengths 108 and 30.4 nanometer in making a transition to ground state. The quantum number n corresponding to its initial excited state of photon of wavelength energy. So for photon energy is given by this relation, and we have to find out quantum number n for the initial state. Now, as we know that when electron makes transition, then it emits photons, and those photons have the energy equal to the gap between those two levels. So here we have two photons with wavelengths. So from that, what we can calculate, we can find out the energy with which they are emitted. So we can say E1 will be equal to Hc by lambda 1, and that will be 1240 electron volt nanometer divided by 108.5 nanometer. Nanometer gets cancelled, and our energy is 11.43 electron volt. Similarly for E2, that will be 1240 electron volt nanometer divided by 30.4 nanometer, and from this we will get 40.79 electron. Now as we can see that here energy difference is such a large value, that is 40.79. So basically this is not hydrogen atom, and it is already mentioned that it is excited helium positive ion. So for helium positive ion, we will have energy formula that will be minus z square into 13.6 by n square, and that will be z is 2 here. So from this, En will be equal to minus 4 into 13.6, that will be minus 54.4 by n square electron volt. So now we have to find levels such that, and as these transitions are successive, means first transition happens from n to some level m, and then transition happens to m to level 1. These are the successive transitions, and we have to calculate this value n. So for the first level, we know for this helium positive ion, energy of the first level E1, that will be minus 54.4 electron volt. For second level, this will be 54.4 divided by 2 square, that is 4 basically, and that will give us 13.6 in negative electron volt. And for the third level, similarly, we will get 6.0 for electron volt. For the fourth level, we will get 3.4 electron volt. So we can see this 40.79, if we subtract both of these two, 54.4 and 13.6, this will give us 8, this will be 0, and this will be 40, so 40.8. And So this transition can't be between level 1 and 2. This transition has to be between level 1 and 3. And if we subtract 54.4 minus 6.04, this will be something around 36. And here we will have 8. Oh, sorry, my mistake. Actually, yeah, this matches with the second transition. This matches with the second transition here. So second transition, that is of where a photon has a wavelength of 30.4 nanometer, is happening between level 2 and 1. So value of n is 2. So now we have to find n such that from that transition happening at level 2 gives us a energy difference of 11.43 electron volt. And I think that is possible between level 2 and 4. If we subtract them, 13.6 minus 3.4, so that will give us 2, yeah, 10.2. So no, that's not right. So means that will be happening either for E5 or E6 or E7. So if we find energy for fifth level, then E5 will come out to be minus 54.4 divided by 25, and that will be something around 2, slightly larger than 2, that is basically 2.18 electron. Now if we check the energy difference between second and fifth level, that will be 13.6 minus 2.18. So that will be 2, 4, and that is 11.12, and that is we require 11.43. So means final level is fifth. So transition is happening between fifth level to second level, and then second level to the first level. So n value of n will be going to be 5 here. With this, let's move to the next one. The electron in hydrogen atom first jumps from third excited state to the second excited state. So third excited state will be n is equal to 4, and from that second excited state, that will be n is equal to 3, and subsequently to the first excited state means n is equal to 2. The ratio of the respective wavelengths lambda 1 and lambda 2 of the photon emitted in this process. So let's say this is lambda 1 and this is lambda 2. So 1 by lambda 1 will be equal to r 1 by 3 square minus 1 by 4 square, and this will be 16 minus 9, that is 7, divided by 9 into 16, 144. And 1 by lambda 2 will be equal to r 1 by 2 square minus 1 by 3 square, and that will be basically r 9 minus 4, 5 by 9 into 4, that is 36. So if I take ratio, I have to calculate lambda 1 by lambda 2. So 1 by lambda 2 by 1 by lambda 1. That is the ratio I'm going to calculate. And that will be 5r by 36. And here I have 7r by 144. So that's r gets cancelled. This will cancel on 4. So this will give us lambda 1 by lambda 2. That is 20 by 7. So option A is the right answer. Moving ahead, consider electron in hydrogen atom revolving in the second excited state means n is equal to 3, having radius the de Broglie wavelength of this electron. Now we know that for suppose this is the nth orbit, and its lambda will be de Broglie wavelength will be lambda n. So here we have a relation that n times the lambda n will be equal to the 2 pi, or basically the circumference, and that radius is Rn. So 2 pi times the Rn. This is the relation we have between de Broglie wavelength and the normal circumference. So here this is second excited state means n is 3, and we can also write Rn. I think, yeah. So no, means actually we can write Rn as n square into a node, where a node is 0.529 angstrom. But I think value of Rn is given to us already, that is 4.69, 4.65. So let us write 3 times lambda n is equal to 2 into 3.14 into 4.65, and this is all in angstrom. So 610, yeah. So this will give us 6.28 into 4.65 angstrom divided by 3. If we cancel this, we will get 155. So 6.28 multiply 1.65, and that will give us approximately 9.7 angstrom. So that will be option D for us. So with this, let's move to the next one. In a lithium positive, electron in the first Bohr orbit is excited by radiation of wavelength lambda. When the ions gets de-excited to the ground state in the all possible way, including intermediate emissions, a total of 6 spectral lines are observed. What is the value of lambda? So it is mentioned that there are total 6 spectral lines, and we know that the formula for spectral line is n into n minus 1 by 2, and it is given equal to 6. So the value of n which is going to be satisfied here, that is equal to 4. So it means that our transitions are happening between the fourth level and the lower levels. Now, as per the initial state, electron was excited. Initially, electron was excited and then it goes to de-excitation. And initially, electron was in the first Bohr orbit. So, what happened? That initially there was some electron and some radiation hit on it. So, due to that, it got excited into the fourth orbit, and from the fourth orbit, it may come down as like this. These are the three, and then from third to second and second to one, and also third to one. So these are the possible way by which electron can get de-excited, and these are total 6 ways. So now we have to find out this lambda which got electron excited from the first to the fourth level. So for that, what we will use hydrogen's energy formula for hydrogen like ions, and that is given by En is equal to minus Z square into 13.6 by N square. So for the first level, we will have minus of 9, because for lithium, the atomic number will be 3. So 3 square is 9 into 13.6 divided by 1, and that will give us minus 122.4 electron volt. Now for the fourth, we will have minus 9 into 13.6 divided by 60, and this will give us minus 7.65 electron volt. So now the difference here will be E4 minus E1, that will be equal to 114.75 electron volt, and from this difference we can calculate lambda. Lambda will be equal to Hc by delta E. So that will be 1240 electron volt nanometer, that is value of Hc, divided by delta E, that is 11475 electron volt. So electron volt get cancelled, and our answer is 10.81 nanometer, and that is nearest to the option D here. Now let us move to next one. Taking the wavelength of the first Balmer line in hydrogen spectrum, n is equal to 3 to n is equal to 2 as 660 nanometer, the wavelength of the second Balmer line. So for the first Balmer line, we can write that 1 by lambda, that is already given 660 nanometer, will be equal to R 1 by 2 square minus 1 by 3 square. And from this we can write 1 by 660 equals to R times 9 minus 4, that is 5, divided by 36. Now for the second Balmer line, it will be, expression will be like this: 1 by lambda R into 1 by 2 square minus 1 by 4 square. and this will give us 1 by lambda is equal to 3r by 16. Now if we divide both of these, then we will get 1 by 660 divided by 1 by lambda is equal to 5r by 36 divided by 3r by 16. So that r gets cancelled and we have 4 and 9 here. So basically this leads to lambda by 660 is equal to 20 by 27. So lambda will be 660 into 20 by 27. Now we can cancel it on 3. That will be 9. That will be 220. So answer will be somewhere around 440. How? We can approximate it like this. That 220 into 20. We are approximating and we are approximating 9 as 10. So what will happen? We will get 440. So answer will be something around 400. And as we have increased the denominator, so actual answer will be greater than this. If we had decreased the denominator, the answer will be smaller. So from that we can conclude that option B will be the right answer. Moving to the next one, a helium positive ion in first excited state, its ionization energy is. So helium positive ion is there. So for that we can write En is equal to minus of 13.6 Z square by N square. For helium positive, Z is 2 and it is in first excited state. So for first excited state, N is also 2. So this will be minus 13.6 into 2 square divided by 2 square. So these two cancel and the energy of the second state or the first excited state will be minus 13.6 electron volt and ionization energy will be modulus of this, that is option C. Moving ahead, radiation coming from transition N is equal to 2 to N is equal to 1 of the hydrogen atom fall on helium positive ions in N1 to N2 states. And the possible transition for the helium ions as they absorb energy from the radiation. So here what we have hydrogen atom. There is transition happening and due to this transition we are getting photon and that photon strikes on helium positive ions. So now we have to find out that what is the possible transition which may excitation happens which may happen in helium positive. So here we have in hydrogen we have de-excitation and in helium we have excitation. So let's solve for hydrogen first to calculate the de-excitation energy or the energy carried by the emitted photon. So from N2 to N1, we can just simply use formula that En is equal to minus 13.6 Z square by N square. Now for hydrogen, we know E1 will be equal to minus 13.6 electron volt and E2 for the second level it will be minus 3.4 electron volt. So delta E, the energy of this photon will be equal to 10.2 electron volt. Now we have to find out two levels in helium positive ion which have the same energy cap. So for helium positive ion, what we will have En is equal to minus 13.6 into Z is 2, so multiply 4 divided by N square. Now E1 will be minus 54.4 electron volt. E2 will be basically minus 13.6 electron volt and E3 will be minus 6.04 electron volt and E4 will be equals to minus 3.4 electron volt. Now we can see that E2 and E4, 4 helium positive ion have the same band gap or same energy level difference which hydrogen have for the first and second level. So the difference between the energy level will match and the transition will happen between second and the fourth level. And that is our answer for as option D. Now let us move to one more question. A hydrogen atom initially in the ground state is excited by absorbing a photon of wavelength 980 angstrom. The radius of the atom in the excited state in terms of Bohr radius A known will be. Now here we have to find out radius of the atom. So we don't have to calculate the nuclear radius. We have to calculate the electronic radius. And we know that for electronic radius, we have R is equal to N squared times A naught. So now let's find out the energy of this photon. So we can write that E is equal to Hc by lambda, that is 1240 electron volt nanometer. And here lambda in nanometer will be 98 nanometer. So nanometer gets cancelled. And let's approximate it as 100. I'm approximating it as 100. So 1240 by 100, and that will be something around 1.24 electron volt. So we have to find two levels in hydrogen atom which have the energy difference or energy gap of 1.24 electron volt. Oh, sorry, my mistake. It will be 12.4 electron volt. That will be 12.4 electron volt. So for the first level, a hydrogen atom has an energy of minus 13.6. For the second, it will be minus 3.4. For the third, it will be minus 1.51 electron. And now if I match these two, if I find difference between first and third, that will be 13.6 and 1.51. So that will be 9. And here I will have 12.09. So I think it may be a possible answer. Let's check for E4 also, and that will be negative 0.85 electron volt. And how I calculate this? That will be En is minus 13.6 by N square electron volt. So now for the first and fourth level, what we will have, and let's discuss it later. For first and fourth level, we will have 13.6, and here we have 0.85. So this will be 5, 15, 7, and here I will have 12.75 electron. Now, how to decide between first and third and first and fourth, because we are using approximation. So as we have increased the denominator. So actual value will be slightly higher than our approximation. So actual value may be 12.5 or 12.6, and the answer nearest to them, and that is 12.75, means the transition is happening between first and fourth level. So using this formula, our radius will be 4 square times A naught, that is 16 A naught. So option C is the right answer. With this, we end this video here. Hopefully whatever we have covered is helpful to you. Again, if you have any doubts or suggestions, you can put them in comment section. I will try to resolve them. And if you find these videos helpful, then do press the like button, share them, subscribe to our channel. Want to support us financially, scan the QR code in front of your screen. With this, again, thanks for watching, and we will meet in next video.